In the slides I posted today, we get into the topics of recursion and iteration. It's really uh, programming that allows you to execute a statement over and over and over again. In these kind of voiceover lecture, today I'm going to talk about recursion. And prior to that, I'm going to review conditional execution and functions, as well as incremental development and what's called scaffolding code. First, in kind of a not quite a non sequitur, but a disjointed bit, mention one built-in function called isInstance. And it makes sense given what we've learned about Boolean expressions. So expressions that involve values and logical operators that can be evaluated to give you one of the Boolean values of true or false. So this built-in function isInstance takes two parameters. The first is a value, and the second is a data type. And if the argument passed for that first parameter is an example of the data type that's passed for the second parameter, the output value, the output Boolean value, is going to be true. If it is not an instance, then the output will be false. So here in the second time it's called, still passing an argument of integer 2, but here the data type str for string, there are no quotes around this 2, and so the answer is false. In this third example, our 2 is enclosed in quotes, and so it is an example of a string value. Here, the number 2 has no decimal point, and so it is not an instance of a floating point number. 2.0 would give us a true. 2.1 is an instance of float, so that's true. We'll see later on how use of this built-in isInstance function can help us screen for unwanted, non-valid input values in our function. So quick review. What is a Boolean expression? I said it just a minute ago. It's an expression, a series of values, operands, and operators that can be reduced to a Boolean value of true or false. It can be evaluated to that single value. Truthy, you don't hear falsy as much, could. Truthiness also makes use of Boolean operators. So those logical operators, the Boolean values of true and false. But it does so in a different sense than a lot of other conditions, where the true and false make kind of the intuitive reference to correctness. Instead of that, truthiness is a quality of variables or values directly that refers to the kind of there being something there. So we saw that you can evaluate the truth of a string, some sort of characters enclosed in quotes, or you can evaluate the truthiness of numbers. And for the number 0, that is a false number. Not in the sense that it's correct or incorrect, that doesn't really make sense, but in the truthiness sense, it would. Similarly for strings, if there are any characters at all enclosed in quotes, that string is considered true. But if it's an empty string, no characters within the quotes, it is false. Second point here, what's the structure of conditional execution used in Python? Well, we saw that using the if and then a condition and then a trailing statement that would be executed only if that condition were true. We can also make use of the elif token to write out another condition that could be evaluated or could be evaluated and a statement that would be executed if that condition is true, but if the first was not. And we also saw the use of the else token, ELSE, which accounts for um, when none of the listed conditions are true. And if there's no else statement, then simply no statement is executed as part of that branching, and the interpreter would jump to the next line, back to the initial indented order. So no tabs in, so to speak. And then 3, let's just kind of evaluate some Boolean statements on our own. So true and false, so this being kind of a logical operator, and think of it as the equivalent to the intersect, which requires both of the operands to be true in order for the evaluated value to be true. So if one of those is false, that's enough to render the whole expression false. 17 less than or equal to 18, that's true. False or false, so or being equivalent to the union. If either one of those would have been true, then the resulting expression would be true. But since they're both false, the expression is false. 5 less than 3 or 3 greater than 5. So this can be evaluated to true. There we go. That would be evaluated to false. And for true or false, only one of these needs to be true. And since we have one of them, that expression is true. And then not 5 greater than 3. Since that is true, the opposite, or not true, is false. One more thing to review, fruitful functions. So these are functions that return a value. That value can then be used in other functions in the script. Most functions that are useful to us would be fruitful in that they return a value, but not all are. They all do something. Some examples of functions, of what functions that don't return a value do. They might print something to the console, could move a file on the operating system, or call another function that does any one of these things. Those are called fruitful functions. Now expanding beyond what we've reviewed, getting into more matters of technique or how you code. We'll take up the topic of incremental development, kind of the AKA for this, the other way of saying incremental development, or really the justification for doing so, is to develop code in a way that doesn't cause you to lose your mind. So lose your mind or lose track of variables, of values in the script. Kind of just doing a little bit more typing, as the case will be, in order to better lay out all of the variables you're going to rely on. So one of these examples that we'll use is that of calculating distance between 2 points in kind of a Cartesian plane, xy space here. So kind of we got input parameters, 2 points with x and y values measuring their coordinates. And what's returned? Euclidean distance between the 2 points. And we use this kind of square root of the sum of squares of the differences measured in each one of those dimensions, x and y. So this function here, defining the function distance, takes 4 parameters. So x and y coordinates for 2 points, 2 times 2, 4. One line within that, return math.square root. We've imported math right up at the top. So the difference in the x's to the power of 2 plus the difference in the y's to the power of 2. And then it's called. So that could be a script, and it would do what it needs to do, calculate the distance. But, if you got into, theoretically more difficult math, but also just syntax, like the characters of the math could be very confusing. You might lose track of parentheses. I don't know, have a single asterisk instead of two. And if you had a single asterisk here, it would work, but what would happen is that would be multiplied. So you could have some semantic errors where your code would still run, but you're getting the wrong answer. Or your code could simply not run because you have to type out too many characters. So even if this function works, it might not be ideal, and it might not be something that you would type letter by letter to get there. Instead, in incremental development, you break up complex problems, multi-step problems, to do them one at a time. So the code on this slide, slide 8, is doing the same thing. So we're still writing a script to calculate distance between 2 points in XY space. We're still defining that distance function for parameters. But here, we don't just cut to the return line. We still have that at the end, return result. But what is result? We can work backwards. Result is the square root of something called d squared. So the variable d squared assigned a value dx times dx, dy times dy, and each one of those variables is defined on a prior line as the difference between the two x coordinates and the two y. So instead of just one line, we're working with 5 lines of code, each one of which does essentially one different operation. So we have a subtraction, subtraction. I guess this is multiplication and sum. It's a sum of the squares. Here's the square root, and that itself is assigned to a variable. So here, instead of, here we have just the parameter names themselves. We have no intermediate variables. In this script, we have 4 of them. So dx, dy, d squared, result. It's a lot more typing, a few more lines, but every kind of step in the process is laid out for us to see. When you're writing that, a script like that, kind of step by step, in order to check that you've got that step right, it might be helpful to run the print function to print out the value of these temporary intermediate variables, things like dx, dy, d squared. So as you're writing it, you'll, given kind of the specific arguments that you pass as parameters, the specific input values, you're going to have an idea of what the difference should be. And so when you print that out, you'll see in the console, the idle console, or whatever development environment you're working in, the value of dx, and you can check that against your assumptions, your expectations, so that if you have a problem, you can catch it early on, and you can isolate it. You can figure out where in the script your problem's coming from. And what you would do after is simply delete or comment out the print statements so that they don't print it every time the script is run. Here's a function. Moving on to the topic of composition, the process of calling one function from within another function. This script takes 2 points, one the center of the circle, and another the P point, a point on its perimeter, and it returns the area of the circle that's defined by a given center and a given perimeter point. So there are 3 functions defined, and it's called, the calc area function is called, with a center point, cx and cy of 0, 0, and a perimeter point of 0, 1. So when that function is called, calc area, we look up to where that function is defined. a variable named radius is being assigned the output of this distance function, passing these same 4 arguments to the distance function, which is defined here. So this example, kind of the calc area function, calling the distance function that's defined right below it, is an example of composition. So these cx, cy, px, py are then going to be passed as the x1, y1, x2, y2 parameters for the distance function that we just took a look at, that takes the square root of the sum of squares. And then, once the value of radius is determined, it's used as an argument for this area function, which is defined down here and returns the value of pi times the input radius to the power of 2. And so here we've taken the script we worked on for the last few minutes, this distance function, call that within a new function called calcarea that also relies on this kind of pi r squared function that we worked on last week. And then finally, the output is printed out. Within a function, you can call other functions. Moving on now to the topic of recursion, we see that not only is it legal or allowable for one function to call another, but it's also legal for a function to call itself. And we see this for a good, this is called the process of a function calling itself is recursion. And we can see it well through this countdown function here. Define countdown, a function with one parameter n. Now go within the statements of the function. There's a condition. If n is equal to 0, print the word blast off. But if not, print what n is, and then run the countdown function using an n that's 1 less. So let's see what happens with this. File, new file, move that over, define countdown n. If n equals 0, if that's true, print blast off. Put that in quotes, string. Else, print the value of n, so no quotes, it's just going to print the number. And then I'll count down again for n minus 1. Then let's, in the script, call countdown with an argument of 5. Save that. Blast off. Ah, forgot my parentheses for the print function. There we go. So the output is 5, 4, 3, 2, 1, blast off. When we look at this function, we have an if-else branching, and these two sections of code are different cases. The last one that executes is referred to as the base case, others as the general case. We look back at the script here. When this function is first called, n is equal to 5. 5 is not equal to 0, so blast off is not printed. Instead, 5 is printed, and then countdown is called with an argument of 4. 4 is still not equal to 0, so we skip to here, and the number 4 is printed right there. Then countdown is executed, is going to be called here. with an n equal to 3. 3 is not equal to 0, so 3 gets printed. Countdown with an argument of 2 is called. 2 is not equal to 0, so the 2 gets printed, and then so on with 1. And then after it's called with 1, countdown the value of 0 is called. And when it, on that base case, n is indeed equal to 0, so blast off gets printed, and then countdown is not going to be called, because if this condition is true, then this statement executes, and everything in the else block of code is skipped. So if we raise the value of the argument there, we start higher. Another example of recursion that's common in math is called the factorial function. So in this factorial function, which is marked or described by an exclamation mark after the input, a factorial of 0 is set equal to 1. A factorial of any other integer, positive integer here anyway, is going to be equal to that integer and then the factorial of the integer 1 less. So for factorial 1, it's going to be 1 times factorial 0, or 1 times 1. For 2 factorial, it's going to be 2 times the factorial of 1, so 2 times 1. For 3 factorial, first it would be 3 times 2 factorial, and 3 times 2 times 1 factorial, and that can be reduced to 6. So this is a function that increases rapidly. This is how it would look if we type it out in Python. Define factorial with one parameter n. If n is less than or equal to 1, return 1, the base case. Since factorial 1 and factorial 0 are both equal to 1, you can kind of make that a little simpler. Else, return n times factorial n minus 1. So this is a fruitful function. Doesn't print within the function, but it's recursive because this function called factorial calls itself, and it will repeat, it will execute this statement over and over again until this condition is true. We can type that out. Define factorial n if n less than or equal to 1, return 1. Else, return n times factorial n minus 1. Did I get that right? Yep, I think so. And then we'll print out we won't do all of this. 2 factorial is factorial argument of 2. Print a little higher. 6 factorial is factorial 6. Try that. Factorial 2 is 2. Factorial 6 is 720. So yeah, it increases quite large, quickly. So there is something called infinite recursion, and it's not good. This is when a function calls itself, or it never reaches a base case. Instead, it goes on making calls forever. Excuse me, I just found a typo here. So here, in theory, then the program would never terminate. In practice, it does, just because the computer stops executing the code if it does the same thing over for a few thousand times without changing any inputs. So in this example that I just amended to add in a function call within the else statement, if n is not equal to 0 initially, there's no change to the argument that's passed. In our factorial example, the function is called again, but you have a different value passed as the parameter, as the argument for that parameter. It's not n, it becomes n minus 1. If you keep it n, it's going to call itself again and again, and this general case, printing of n, is what's going to happen every time. It doesn't get closer to blast off. It stays the same. Instead, you need to modify the argument. Let's see. Go back to our blast off. And we'll call it countdown. That was the name of the function. See how that goes. Always forget my parentheses. Let's see. Oh, left out a T. Here we go. So there's the blast off function. Oh. Here's a blast off function that works as intended. Countdown 5, n equals 0. There we go. There is the countdown function that works as intended. If I eliminate that -1, the downward incrementing of the argument, and then I run it, what will happen is 5 keeps getting printed, in theory, forever. We'll check in on it in a few minutes. Be there. So you can pause this and then, as an exercise, working on the factorial example, can write a recursive function that, instead of multiplying, takes the sum of the first n positive integers, where n is given as an argument. Yep. So here, finally, maximum recursion depth exceeded while pickling an object. So new script, working off our factorial example, but we'll call this sum int n. If n equals 0, so that's the base case, else, and then we'll call that function sum int the value of 5. So if we're calculating the sum of all the integers up to 5, it should be 1 plus 2 plus 3 plus 4 plus 5, 15 is the example we want. We're going to write one line for the base case, if n equals 0, else what it gets returned. So for our factorial example, if n equal or less than 1, return 1. Else, return n times factorial. In the factorial example, the base case is returning 1. And in the general case, you see n times the recursive function call. So if we instead want to sum the integers, we're going to have a little bit different base case and a little bit different general case. So for the base case, the sum of all the integers up to 0 is going to be 0. It's not going to be 1. And in our general case, we're not going to multiply or take the product of these, but we're going to sum them. And then what did I say? The anticipated output of the sumInt function passing an argument of 5 should be 15. Did that work? Ah. There we go. Keep getting ahead of myself. There we go. Ah, 15. Eventually it comes out. So I didn't have the print function. So this sumInt is a fruitful function. It's going to return a value. If n is 0, it's going to return 0. Else, it returns n, the number itself, and then the sum of all the integers less than it. So the first time this is called sumInt 5. 5 is not equal to 0, so we skip to this statement right here. 5 plus sumInt 4. Then sumInt 4 is called. 4 is not equal to 0, so it's equal to 4 plus sumInt 3. And so we finally see 5 plus 4 plus 3 plus 2 plus 1 plus eventually, this base case is met. We see a plus 0. And then that's what gets printed. Now, once we have our function written as such, though, what happens if we put in a negative integer? Let's see. Oop. Getting an error. And it's not for lack of trying. Maximum recursion depth exceeded. So it kept running until it kind of hit the fail-safe and stopped. Kept running because if we start at -5, -5 is not equal to 0, we'll cut to the general case, but it will be -5 plus sumInt -5 minus 1, or -6. And so the n, or the argument, is going to be moving away from 0, away from the base case. And it's just going to run and run and run until it stops. So we could tailor this to negative inputs by putting a +1 there. If we run that, we simply get -15, because the value of this argument is going to go toward 0 that defines the base case. But we don't have to tailor a different function. One way is to add in a different condition. So if n is equal to 0, that's the base case, return a 0. Or if n is less than 0, if it's -5, just return a string saying this code is not going to work for you. put in a positive number. What happens when we do that? Elif n is less than 0, return, I misspelled that, return, enter a positive digit. And now, we run that, we get that message, which alerts the user as to an error and describes kind of what needs to happen for it to be remedied. I'm going to skip these slides on the Fibonacci sequence. It could be illustrative for other recursive function calls. But back to our factorial, and we can do this for our sum of integers example as well. Making use of the isInstance function is another way that we can guard against kind of unwanted or improper input values. So in this factorial function, the base case here is put on an elif line because it's simply just not the first condition that's going to be evaluated. Instead, this if not isInstance n integer, or n is less than 0. So there's another pitfall here. Even if we use a positive number, if we put 5.1 and run it, going to keep running, and we don't get a decent output because 5.1 minus 1 minus 1 minus any number of integers is never going to be equal to 0, so the base case isn't met. So to avoid both of those, you could set up a logical expression. So if either one of these problems, n is negative or n is not an integer, is true, then print input must be an integer. Return -1. This is kind of a convention. Sometimes you'll see a -1 returned or -99, something that should indicate an out of the usual, out of the ordinary result of the function. Finally, just to kind of sum up, recursion, the function calling itself, can be used to accomplish tasks like calculating mathematical sequences, factorial, sum of integers, Fibonacci sequence, or anytime you just have a general case and a base case that you want to apply in kind of the last instance. In my next lecture video, I'll talk about iteration. It's a similar kind of way to structure your code so that statements repeat or are executed more than once, but it does so in a way that it carries out a task multiple times but functions a little bit differently. Basically, if you have an ordered sequence of inputs, it could execute a statement for each one of those inputs, or it could simply execute a statement whenever or while a condition is true.